Industry projections for the total cost of global AI infrastructure are climbing towards $7 trillion. This staggering figure is driven by an uncomfortable admission from an executive at NVIDIA. Right now, the compute power required to run these models is more expensive than paying human workers. The standard way we build AI relies on a massive bottleneck. For a clinician in rural Mississippi or a cocoa grower in Ghana to use these tools, they have to transmit data over reliable broadband, a utility that billions of people simply do not have. If the data can be sent, it travels to centralized data centers. These facilities consume massive amounts of electricity and capital to keep thousands of processors running around the clock. The hardware driving this model is prohibitively expensive. A single high-performance NVIDIA H100 GPU costs up to $40,000. To run a single server with 8 of them, a startup might spend nearly $500,000 before processing their first image. This reliance on centralized power creates a barrier for the 4 billion people living in low-resource settings. Between hardware costs, data transfer fees, and recurring subscriptions, the current path makes life-saving AI inaccessible to the people who need it most. There is also the matter of what is being sent to the cloud. A retinal scan is a unique biometric identifier, as personal as a fingerprint, that reveals a patient's risk for neurological disease and systemic health conditions. Forcing that data onto remote servers creates a massive security risk. In 2024, healthcare data breaches in the U.S. exposed over 276 million records, equivalent to 81% of the population, at an average cost of nearly $10 million per incident. Beyond security, there is the problem of the black box. Conventional AI often issues a verdict without being able to explain its reasoning. If the system can't tell a doctor why it reached a conclusion, the doctor cannot verify if that conclusion is clinically sound. The scale of this transparency gap is now quantified. An FDA review of over 1,000 AI-enabled medical devices found that transparency is abysmal, with nearly half of the approved devices failing to report a clinical study. When an AI contradicts the expertise of a seasoned clinician or a farmer who has spent decades reading their own soil, and that AI cannot explain why, the only rational response is to ignore the system. To solve this, we have to ask a different question. What if the AI never left the building? What if it never needed to? Standard deep learning is a computational sledgehammer. It treats a medical image as raw pixels, using millions of parameters to statistically guess disease patterns. A different approach, virtual spectral decomposition, acts like a scalpel. It applies specific mathematical functions to isolate the exact biological signals a clinician looks for. VSD breaks the image into distinct layers. One channel isolates vascular health, another structural changes, a third pigment shifts, and a fourth anomalies. This architecture turns the AI from a black box oracle into a transparent tool. It speaks the same biological language as the human expert, showing its work in a way that can be interrogated. Instead of giving a vague confidence score, this system evaluates those biological channels and produces a simple 4-bit binary code. A code like 1001 tells the clinician exactly what the system found. The vascular and anomaly axes have fired, while the structural and pigment axes are clear. By providing these specific markers, the AI provides the reasoning, but the human makes the decision. A doctor can directly look at the original image and independently confirm the hemorrhage or vessel tortuosity with their own eyes. Because this method removes the need for massive statistical guesswork, the computational cost drops. The entire process runs in under 1 second, completely offline, on a device that costs under $100, like a Raspberry Pi. This level of interpretability isn't just about trust. It provides the mathematical efficiency needed to run AI without a multi-million-dollar data center. This creates true data sovereignty. Because the processing happens locally, the patient's biometric data or the farmer's yield records never leave the device that captured them. When the data stays in the room, the legal overhead of compliance frameworks like HIPAA or GDPR is drastically reduced, and the risk of a third-party server breach is eliminated. This enables a 3-tier deployment model. At Tier 1, we can perform population-level screening using nothing but offline smartphones or handheld sensors. No internet connection is required. Tier 2 covers portable clinic stations. The expensive cloud infrastructure at Tier 3 is only used as a last resort. reserved for complex cases where the system produces an ambiguous code that needs review by a remote specialist. This model allows AI to scale with hardware rather than software subscriptions. If one device in a village breaks, the rest of the network keeps working. There is no single point of failure. The AI industry is currently built on a model of recurring revenue and perpetual infrastructure. A localized system replaces that with a one-time hardware cost. The goal is not to replace human expertise, but to build a system that speaks the same language as that expertise. It provides the biological reasoning and lets the expert make the call. By dropping the marginal cost of compute toward zero, we can finally get working diagnostic tools into the hands of the 4 billion people who have been left out of the AI revolution.